C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metravib, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metravib's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research, simplifying thermal conductivity.
All right. Good day, folks. Thank you for joining us for today's webinar. We'll be getting started with the formal session here in about a minute or so. Just wanted to give a few, I guess, housekeeping items. So today's session will be recorded and available for playback at the end of the session. If you have to drop off early, or maybe you have some colleagues that weren't able to make it, you can certainly send them a link and they can review this at a later time. For those who will be with us here live, please feel free to make use of the chat box feature. We will be going into a Q&A session at the end of today's session, going over a few different, any questions that come up, whether it's related to the content presented here, or maybe something more specific to the work that you're doing yourselves. So definitely feel free to interact with us and ask any questions that you might be interested in. All right, so I believe, yep, about a minute or so past the hour, so let's jump into it here. Here we go. So today's webinar, titled DMA Applications in Polymer Composites. This will be led by my colleague, Arya Shahrostambeik. He is a laboratory technologist here at C-Therm Technologies, with a lot of background info on the DMA system. Myself, Arya Hakimian, two of us at the company, so I'll be just here to do a brief introduction, running us through a little bit of a setup for today's talk, and then going through the a little bit of an outro near the end as well. But that being said, for those who may not be familiar, just want to give a little background, a little introduction to who C-Therm is, what we do. So primarily we are experts in thermal conductivity testing, with a focus on transient methods. Really, our goal, reason for being, is simplifying thermal conductivity testing for the materials of tomorrow. But of course, we also work with various partners, such as Rigaku and Metravib, for other material characterization. And of course, the Metravib DMA is what's going to be the main focus for us here today. Did just want to highlight very briefly, if thermal conductivity was also potentially of interest to you, our Trident platform is our main instrument. It's a modular system for the measurement of thermal conductivity and related properties. It's modular in its design, and the idea behind that is, again, being able to pick and choose the best tools for the task at hand. There are 4 different methods that are available on this platform. And again, while it won't be the focus of today's talk, if you did have any questions or wanted to learn more about these methods, feel free to shoot us a question in the chat box, or definitely make use of some of the previous resources on this specific application through our content on our website. So, I'll just maybe speak briefly to the ideology behind the development of Trident. This quote here from Abraham Maslow is something that really embodies it. When all you have is a hammer, everything looks like a nail. And again, it was kind of mentioned in that intro video, but the idea here is that if you're locked into one way of doing something, even though it might work really well for a certain set of materials or testing conditions, it can sometimes fall short in other scenarios. So being able to pick and choose the best tool for the task at hand is really what we try to advocate for here. Again, having the ability to switch to something that's maybe more geared towards solids or liquids or high temperature, for example. And again, if you did have any questions, happy to discuss that further. If you're new to thermal conductivity or like material characterization, we do have a method selection guide available as a free resource on our website. This is available for download. Definitely feel free to make use of this. It's even good just to review for those who maybe have some experience as well, but maybe want to see how they compare to each other. It's a nice resource that covers some broad strokes there. And then, yeah, as I mentioned, so we also partnered with Rigaku and Metravib being the key focus of today's session for their DMA. I will also mention, for the folks that are maybe interested in doing some material testing, we also have a full-service contract lab, thermal analysis labs, which offers all of the capabilities we have here at C-Therm, amongst others, as well as the Rigaku and Metravib systems. So if you did have any needs for testing, looking for a group to help you out with those requirements, again, feel free to reach out. So if you'd like to learn more, maybe you want to do a little bit more of a specific deep dive on some of your applications of interest. Again, whether it's related to conductivity, the Rigaku thermal analysis line, or DMA, please feel free to reach out. We'd love to book more of a technical consultation with you where we could go into these in further detail, and again, specific to what you're looking at in your for your projects. And also maybe if you like what you see and you want to get some costing information, we can certainly provide a quote if that's something you're interested in bringing in-house. So I'll finish up here with a client testimonial. We always like to really kind of highlight what our clients are saying. This one here from Dr. Enrique Jackson from NASA. So he mentions they purchased the C-Therm thermal conductivity analyzer after seeing a demonstration. The instrument provides unequivocal results and provides the flexibility to test powders and liquids. So having that flexibility was key to this group. In terms of our satisfaction with the purchase, I give it a 10 out of 10, extremely satisfied. So always nice to hear what folks have to say. And if you are interested in maybe seeing what other people are talking about the instrument, there is a list of these testimonials available on our website. But, enough of the intro there. I'm going to pass it over now to Arya to go really through into the bulk of today's session on DMA. So at this point, Arya, I'll stop sharing here and welcome you on screen to take us through the body of today's talk. Thank you.
Okay, well, thank you so much, Arya. Hello, everyone. Welcome to today's webinar. We're so excited to have this webinar today with you, and so let's get started. So today's webinar title is DMA Applications in Polymer Composites. So in order to understand the title better, let's break it down into two different portions. So the first one is DMA, and the second one is Polymer Composites. So DMA stands for Dynamic Mechanical Analysis. It's a mechanical test, but what is really polymer composites? What material we're dealing with? So the short answer to that question is basically almost everything. In today's industries, you can find different polymer composites in different applications, for example, ranging from aerospace to automotive, construction, biomedical, sport equipment, electronics, and packaging. So almost everywhere you look at, you can find one polymer composite. So it's very important for us to understand polymer composites properties at different conditions, temperature, pressure, and how they behave under different conditions. So again, if we go back to title, now it's time to talk about DMA, or Dynamic Mechanical Analysis, and understand what it really is. So Dynamic Mechanical Analysis, or DMA, is a powerful tool to measure the viscoelastic properties of materials, including filled or unfilled polymers and rubbers. Basically, when speaking about composites, we're talking about material that they are blend of two components at least. These two components can be from different sources. And so viscoelasticity is the property of both viscous and elastic characteristics when undergoing a deformation. Viscoelastic properties are unique to DMA, meaning that not any other instrument can measure those properties, and DMA is a powerful tool that is capable of measuring those viscoelastic properties. Metravib provides different instruments to analyze viscoelastic properties of the material using DMA technique, and it provides a wide range of characteristics and features such as frequency. They're providing the highest force available on the market for today's application, and they've been making effort in order to improve dynamic mechanical analysis testing for over 40 years. Their instruments can cover a large variety of the materials, from large stiffness to low stiffness, from low frequency testing to high frequency testing. This is an important part of a DMA that you want to run your test with, because you want to make sure that you understand your material and its properties properly. So as I mentioned before, there are a variety of instruments they can run DMA tests. We can start from desktop series, which provides lower force compared to others, and the plus series, which provides high frequencies and high forces up to 2,000 Newton, and automated option and capability of running the fatigue testing, and finally a high frequency analyzer, which is capable go to 10K hertz. So as I mentioned before, you have lots of options for different variety of tests and to better understand your material's viscoelastic properties. But let's talk about DMA principle and understand what's going on behind this technique. Dynamic mechanical analysis is the most accurate technique for measuring viscoelastic properties of material. DMA consists of applying a dynamic force, excitation to a specimen of material, measuring the applied force and the resulting deformation. It is important to note that, unlike static tests where a constant load is applied, a dynamic periodic load is applied for these testings. It is important to mention that, mentioning this fact that DMA is the most accurate technique for measuring viscoelastic properties can be very, very crucial. For example, one of those properties can be derived from viscoelastic properties and can be measured is glass transition temperature. So I'm going to explain more in details about glass transition in the next slides, but just to mention this fact that glass transition temperature with DMA can be measured 100 times more accurate than any other methods. And just let's take a look at this figure provided in this slide. So you can see a DMA is applying a dynamic periodic load on the sample, and it's deforming it. So you can see the force that is being applied on the sample and the displacement that is recorded. And you can see that there's a phase angle, or there's a delay between the force that is being applied on your sample and the response or the displacement followed by the force that it has been applied. So this is very important for us because this is exactly the viscoelastic property of the material that it is very important and crucial to understand material. But let's understand what exactly viscoelastic means. So I always use this illustration to explain viscoelastic properties. So imagine you're holding a ball in your hand and you want to drop it. So after you drop your ball, you see that the ball doesn't bounce back up 100% to the same height that you released it initially. So we have loss of energy, and to some extent, it does bounce back up. So the amount of energy that has been stored in the ball that it is making it capable of going back up is called storage modulus or elastic modulus. So it's basically the capability of the material to store energy and return it. The other portion of the energy that has been dissipated through the matrix of your material is called loss modulus, and is dissipated through heat. And the combination of these two is called complex modulus. So basically, this is the basics of viscoelastic properties. This is another figure explaining the same phenomena, and this is related to viscoelastic nature of the material. And as I mentioned before, we have the same graph on the right side, and you see that depending on the material, phase lag can be different, or the delay in response of your material can be different. The more stiffer the material is, the higher storage modulus. So it's a more stiff, it's brittle, so it's more capable of returning that energy you're applying to. And the more viscous your material, the softer the material, and more ability to dissipate energy through the matrix via heat. So in order to deform the sample to record different data from the test, there are various excitation modes. Here we see 4 main excitation modes, which are tension, compression, shear deformation, and bending. Today, we are going to be focusing more on tension, compression, and shear. So the fact that there are different deformation modes based on different application, it makes the DMA very flexible analysis technique to address the large variety of materials, including thermoplastic polymers, thermosetting polymers, rubbers, even metals, ceramics, films, and paints, and even liquids to be tested on a different mode. And so to wrap up whatever we have learned so far, we got 4 main components while running a dynamic mechanical analysis test. So a complex modulus, as we said, is the resistance of a material to a deformation, which is the ratio of stress to strain for viscoelastic material. The elastic or storage modulus expresses the ability of material to store the energy. And viscous modulus or loss modulus expresses the ability to dissipate the energy through heat. And there is another important ratio for us, which is called tan delta. So also is called loss factor, which is simply the ratio of loss modulus over storage modulus. Material damping can show itself through this ratio, and this is very important. I'm going to explain more about it in the case studies. So let's first, before jumping to the case studies, talk about glass transition temperature that I mentioned before. So basically, glass transition is the second order transition in the material. So it means that we don't have change in state of the material. So the material is still in solid state. However, the material, better to say, the more viscoelastic material, like for example, polymer, gain more energy and enough energy. So it makes the chain able to actually move around. So the material structure gains mobility. So your material usually becomes softer. So it has more freedom to move around. So based on this temperature, this is very important to know that because it can change the behavior of the material. And it's important to understand the properties of the material and that temperature point. So initially, the typical method to measure glass transition temperature was a differential scanning calorimeter, or DSC. And so, but after DMA testing and experimenting different tests with DMA, it was shown that actually DMA is 100 times more accurate in finding glass transition temperature. And so as you can see, we have 3 plots here on the left-hand side, on the second axis on the left. On the y-axis, you see loss modulus, and you see tan delta in the red, and on the right side, you see elastic modulus or storage modulus. So we see that with approaching the glass transition temperature, there's a drop in elastic modulus, which is anticipated, and you can obtain glass transition temperature by that drop or by loss modulus or tan delta. It shows itself in a peak in tan delta. And so the drop in elastic modulus is called the mechanical approach to find glass transition temperature. And the loss modulus is the closest one to what DSC method is used to obtain glass transition temperature. However, the principle is different, but that's the closest approach. And it's called for DSC, and the tan delta method, which is the most sensitive one, is used by DMA, and it's called chemical approach. And as you can see, there is a significant difference in that temperature. So it is important that have reliable information on that temperature based on a different behavior of the material that I mentioned before. This is another illustration of glass transition temperature for the viscoelastic material. So as you can see, it is storage modulus plotted over temperature, and you can see the glass transition temperature that shows itself with a drop in elastic modulus. But if you keep going to the lower temperatures, you see different transition. For example, beta here is the side chain movements, and all the other local movement or stretching of the chains of the polymer, for example. So these are very neat properties of the material. However, it is very important to note that neither TMA or DSC or any other instrument is sensitive enough to pick up those transition, and it is only DMA that is capable of measuring and picking up those points and those transition. And another important part here is that, as you can see, in order to reach those transitions, you need to go extremely to lower temperatures. And as you go to lower temperatures, your material becomes stiffer, so you need higher force to be applied on the specimen, so we can deform your sample and we can obtain data. And it's important to have a high force DMA, and this is exactly what Metravib provides with sensitive but high force DMA. You can easily pick up those transitions. So let's go through some case study. The first one is effects of different types of polymer composites, which is filled with alpha fiber. And so just for context, alpha fibers are cellulose-based fibers that are used for enhancing different properties. One of them is mechanical properties. So the experimental setup is explained here. The instrument was DMA 50 Newton that is used for this test. The test is temperature sweep from 0 to 100 degrees C, heating rate 2 degrees C per minute. Excitation mode was tension. And this test was run over frequency of 1 Hertz with a displacement of 10 millimeter. To understand the behavior of this composites, they ran this test, and they wanted to understand how the material behaves as they add more of their fiber along with different compatibilizers. So this is the results. On the left-hand side, you see by adding 10% of alpha fiber to the composite, it has gained storage modulus, meaning that the material has become more stiffer, and followed by adding more fiber, it has become even more stiffer, and it has gained more storage modulus. On the right-hand side, you see the 10% PVC alpha fiber composites has been used, and it's a comparison between different compatibilizers with same composites. And as you can see here, we have again increase in storage modulus or higher stiffness by adding different compatibilizers. And these are the same plots, these are same tests, but the data is plotted over tan delta over temperature. So instead of using elastic modulus, we have used the loss factor or the ability of the material to dissipate energy through its matrix. So you can see that PVC has a higher peak for over the temperature on the left-hand side, and as we are adding more fiber, we have like shorter peak in terms of height. So it means that the higher the peak, the material becomes more softer, because don't forget that on the denominator you have your loss modulus, and the denominator you have your storage modulus. So the more the loss modulus, the higher the tan delta peak, and the softer your material becomes. So as expected, they observe that behavior. And so based on this plot, we can see the glass transition temperature. So the peak of the plot is the glass transition temperature. On the right-hand side, you see different compatibilizers added to the PVC 10% alpha fibers. This is very important to see the difference. Then, as you can see, two of the compatibilizers have changed the stiffness of the material. And the important question here is that why 10 delta is important. Why do we want to draw this plot, draw the temperature over the 10 delta? So let's check the results. It's the same test, but different plots. On the left-hand side, you can see storage modulus, PVC, and other 2% of alpha fibers in the composites. So as you can see, it's really hard to separate the storage modulus plot from each other to have a better understanding of how stiffer our material has become. However, since I mentioned before, 10 delta is very sensitive, and so it can detect small changes in your material and your testing. And as you can see on the right-hand side, you're obviously you are completely confident in separating different peaks from each other, and it's obvious to see that how the stiffness is changing and how the height of the peak is changing. Another important part here is that on the right-hand side, again, is 10 delta. You see that you can easily see that the temperature of glass transition has changed. So you can see that by adding more of your compatibilizer number 3, Ma3, the glass transition temperature has shifted higher. It means that so your material becomes more stiffer. And in contrast, by not adding or adding Ma1, you see that the glass transition temperature actually has shifted to the left, or your material has become softer. So let's talk about the case study number 2, dynamic properties and tire performance of composites filled with carbon nanotube. So carbon nanotube are famous nanoparticles used in different composites. So in this example, we are going to study polymer nanocomposites consisting of tire and carbon nanotube. So experimental setup, they use DMA plus 1000. This is one of those high frequency, high force DMA provided by Metravib. The application was building a master curve, or WLF, frequency temperature superposition. The test was run in temperature sweep between temperature range of -30 to 30 degrees C. The excitation mode was shear for solids, and the frequency of 0.01 to 80 hertz. So the goal behind this test and this research work was to understand the behavior of CNT rubber nanocomposites at high frequencies. So here we see the results. So basically the way that they use WLF or master curves is that you start running your test over a range of frequencies. For this test is 0.01 hertz to almost 100 hertz at different temperatures, starting from -30 all the way up to 30 degrees C. And so based on different temperature and different frequency, you see different data, different behaviors of your material. And based on the WLF model, you'll be able to interpret that data and calculate the behavior of your material at very high frequencies that is actually impossible to measure experimentally. For example, as you can see, the frequency that has been calculated here is 10 to the power 10 hertz, which is impossible to be measured experimentally with the current technology that we have available. So that's a very nice option for us to understand the behavior of material at higher frequencies. And so the calculation is provided is like a built-in option in the Metravib software for the DMA. So you can easily have access. You can start measuring different temperature, different frequency, and obtaining your data and use it for calculation to obtain your master curve. However, it is very important to mention that modeling these properties and calculating these properties is very sensitive. So you need to have very accurate and good and reliable measurement. Otherwise, even smallest errors can lead to huge errors after calculation. So it's important to have correct testing. So another important option that is provided by Metravib DMA is expander or automated solution. The expander is a 6-axis robot arm designed as a flexible automated solution. Currently, the expander automates tests in tension, compression, and shear deformation mode, improves throughput of DMA and fatigue testing, improves accuracy by reducing human intervention, can test finished products or small samples. So the advantage for the expander is that you have control over your tests even remotely. You can do under your samples, your tests under your samples, and it notifies you on your cell phone so you can see when the test was done and when the next test will begin. And you can control it remotely. So another advantage is that you can keep running your testing 24/7, and based on the information that we have from running different tests, there are always human errors. And like, for example, a good instance of that is a clamping sample or mounting sample on specimen holder, which can always come with some errors, and it can significantly affect your measurement. So it's important here to remove this error, and automated solution, we can see that has improved the accuracy of your test. And so as you can see, same numbers, but on the right-hand side, it has significantly improved the standard deviation for both parameters here, modulus and tan delta. And this option is easily provided by Metravib. I have a video of expander I would like to share with you. Yeah, so as you can see, you can place your sample in this area, and there's a kind of like storage for the robot. So robot can go and pick up your sample, it mounts it automatically to the sample holder, and it clamps the sample into correct direction, and it balances your sample and makes sure that all the parameters for a good testing results are provided, and the machine starts running the test. So as you can see, the oscillator force is being applied. After finishing the test, it takes out the sample and use the other one. And you can use tension, shear, and then compression mode. It's fully automated. So for example, this test is compression. As you can see, the sample is being placed between the specimen holder and the force is being applied, and the consequent deformation. Different variety of sizes for sure. And as you can see, the deformation and the test is being run here. So on the left-hand side, you have shear, middle is tension, and on the right-hand side, you can see compression. And it increases the accuracy of your test. Okay, due to the time constraint of unfortunately, I won't be able to finish the video here. Already. Conclusion, dynamic mechanical analysis, as I mentioned before, is a powerful tool to measure viscoelastic properties of the material, including composites and other viscoelastic material. It's very important to understand polymer composites due to their versatile application in today's different industries. DMA is a non-destructive test that apply dynamic periodic load on your specimen, unlike the static test where a constant load is applied. Metravib provides the state-of-the-art DMA available in today's market with the ability of high frequency and applying high forces up to 2,000 Newton in order to understand your material better. Remember that we need that high force for certain applications. For example, running the test at lower temperatures, having high force capability can be very useful. I think there is a few closing steps left that I will let Arya walk us through. Thank you so much, everyone, again, for joining us today.
Alrighty. Thank you for that run through there, Arya. I'll just, yeah, like was mentioned, just going to go into a little bit of an outro here. Again, just after these next few slides, we will be going into the Q&A. So if you do have any questions, I've seen quite a few come in already. Please feel free to stick around for that, and we can go through that together here. All right, so let me just share. Alrighty. So again, if this type of content did, provide value to you and you found it interesting, we do have a range of additional resources, past webinars, different tech write-ups, publication examples, which reference our instrumentation and our partners' instrumentation on our website. So definitely feel free to take a look there. If you want to keep up to date with us, the best way to do that is on LinkedIn. Give us a follow if you're not already doing so. This is where we'll post upcoming webinars, new blog pieces, and various content on really the first place that it will go. I wanted to just quickly run through some of our upcoming webinars. So we've got a few coming up over the next couple weeks. October 1st, we actually have a guest speaker, Michael Strong from MG Chemicals. He'll be joining myself actually to go over some innovations in reworkable thermal interface materials, as we primarily focus on thermal conductivity. So if that's of interest, definitely feel free to join and sign up for that. Later on, mid-October, October 15th, we will be doing more of a deep dive on DSC applications in polymer composites. So kind of a similar topic as what was presented today, but really focusing more on the Rigaku product line. My colleague Genesis will be taking us through that session. And then I guess a couple of days after that, we'll also be doing a thermal conductivity measurements theory and application. So this will be more high level, not necessarily specific to a specific application, let's say. It'll be very broad, looking at thermal conductivity and the different facets and where it can come up. So those are a few posted that will be upcoming over the next few weeks. For those that might be going to conferences over the next little while, just wanted to mention where we will be. October 3rd to 5th, we will be at the Battery Show in India. We have a booth there, so if you are in that region and planning to stop by the Battery Show, we are at booth B252. Happy to have a conversation if you want to stop by and chat. A bit later, so October 7th to 10th, we'll also be at the Battery Show North America, which is held in Detroit. Similarly, we will also have a booth there, booth 3753. And then finally, later in the month, October 27th to 30th, we will be at the International Thermal Conductivity Conference held in Charlottesville, VA. So that booth's still to be determined for that location. All right. Once again, I would like to take this point to thank everyone who attended today's session. Also thanking Arya again for running us through that DMA information there and those examples. At this point, we're going to go into the Q&A session. So Arya, feel free to join me back here on screen. I've seen a few questions come through. So folks who are still staying on the line for this portion, just as a note, I'm going to go ahead and stop the recording at this point, but feel free to stick around to go through that Q&A with us.